So now we will see assignment number 3.b, that is 1-bit SRAM cell using transmission gate switches. So we've already seen how to make the layout for 1-bit SRAM cell using NMOS switches. The layout looked something like this. The only difference between 3.a and 3.b is that we replace the NMOS switches N1 and N2 with transmission gate switches TG1 and TG2, while the middle portion, that is cross coupled inverters, they remain the same. So we already have made the layout of a transmission gate and verified it. So as such, for teaching, we can make two cross coupled CMOS inverters and we can insert the layout of transmission gate twice. But we should note that in the exam this will not be possible because you will not have the transmission gates layout at hand, but you will have to make the transmission gate layout, verify it, and then you can insert it in the layout for 1-bit SRAM cell. And we can see here that every transmission gate has basically three signals associated with it: input, output, and the control signal C. So we see here that the input of first transmission gate TG1 is connected to the SRAM underscore WR, that is a write line, while the output of second transmission gate TG2 is connected to the read line, that is SRAM underscore RD, which is not visible here, but you can understand it. Same time, the cross coupled inverters are the same as before, and the control signal C of both transmission gates TG1 and TG2 are connected together using polysilicon layer, and the control signal C is applied there. And also the output of first transmission gate TG1 is connected to the input of the inverter I1 through a metal 1 to polysilicon contact. Similarly, the input of second transmission gate TG2 is connected to the input of the second inverter I2 through a metal 1 to polysilicon contact. So we will now convert this schematic in front of us into a layout. So we will first make two cross coupled inverters. NMOS, and we will keep them sufficiently apart. We'll put them further apart. Apply VDD, apply ground, polarize the anvil. Now we will save this as SRAM TG switch. Now we will copy this, paste it like this. Now we have to connect them back to back. So we'll select complex contact poly to metal 1, place the first contact here, second contact here. So this is the first inverter I1, this is the second inverter I2. This is the input of I1, output of I1, input of I2 and output of I2. So we connect the output of I1 to input of I2 in this way. Take metal 1, take polysilicon, connect it to the input of I2. Similarly, in order to connect the output of I2 to input of I1, we take metal 1 and we write like this. Connect the contact to the output of I2. Similarly, we connect the contact to the input of I1 in this way. Running a DRC, there are no DRC errors. Now, we will insert the verified layout of a transmission gate. Once more. Yeah. Now we have the cross-coupled inverters in between two transmission gates. So reduce the display and take it here. Take this transmission gate here. Again, place the inverter in middle. Okay. So now as per the schematic, the input of first transmission gate is the write line and output of second transmission gate is the read line. So let us zoom into the inputs and outputs. So here this is the first transmission gate, and we are going to make the input of the first transmission gate as the write line. So we will rename tg underscore in as SRAM underscore write. Similarly, we will make the output of second transmission gate as the read line, that is SRAM underscore read. Now what we will do is we will connect the control signal C of Tg1 to Tg2 using polysilicon. So we have the control signal of Tg1 here and we have control signal of Tg2 here. So we can delete one and we can connect it using polysilicon. So we can take polysilicon here and take it here. And we can connect it here. And we can move the control signal from here to here. Okay. Now, according to schematic, we have to connect the output of transmission gate to the input of inverter I1. So we have the output of Tg1 here and we have the input of inverter here. So we can zoom it first and we can use a contact poly to metal 1. We can put it here and we can connect the output of Tg1 to the input in this way. Take metal 1 here, take polysilicon, connect it here. Okay. So you can refer to the schematic again. and we see that we can delete the TG out signal like this. Similarly, if we refer to the schematic, the output of transmission gate is to be defined. Okay, that is already done. So we have to connect the input of second transmission gate TG2 to the input of the inverter I2. So go here. So this is the input of inverter I2 and we have the TG in here. So we have to connect these 2 points. So what we can do, we can first delete the signal TG in and we have to connect this point to this point. So one way of doing this is that we can take it like this, we can take it like this. Take a contact and we can put the contact here. Take metal one. Similarly, we can take polysilicon and connect it here. There are no DRC errors. Now we have given the input as SRAM underscore WR. Now we can double click this and we can initially give a logic 0 here. We will give the control signal equal to 1 and we can observe the output. So here there are no design rule errors, and for SRAM underscore write as 0, control signal equal to 1. Let us see what is the output. So we see here the control signal C equal to 1 here, write signal is equal to 0, and we are getting the read signal equal to 1.2 volts VDD, that is strong 1. So we see that in the simulation of SRAM cell with NMOS switch, when we had given the write equal to 0, we got a weak 1 at the output, which was not acceptable, but that problem has been solved by replacing the NMOS switches with transmission gate switches, and here we are getting a strong 1 instead of a weak 1. Now we will give the write line equal to logic 1 and we will see what is the output while keeping control signal C equal to 1. So close, double click write line, give a 1, say assign, resimulate. Here with control signal C equal to 1, write line equal to 1 and the read line is equal to 0 volts, that is strong 0, which is acceptable. Let us see what we get if we make the control signal equal to 0. Assign. Now the control signal C equal to 0, write line equal to 1 and the output is equal to strong 0. Close. Let us see what happens if we change the input to 0. So we see here when control signal C equal to 0, when the write line is equal to 0, output is equal to 0, which indicates that if the control signal C equal to 0, then irrespective of the value of write line or the data input, the output continues to remain 0. But the benefit of replacing the NMOS switches as in 3.A with transmission gate switches is that in case of NMOS switches, when we write a logic 0, then we get a weak 1, while in 3.B with transmission gate switches with write line is equal to 0, we get output as strong 1.